Chapter 9, we're going to be looking at three-dimensional figures and doing some like basic geometry stuff within some of these three-dimensional figures. So this first section, we're going to be looking at calculating lengths within a three-dimensional figure. And the idea here, whenever we're looking to find a length inside of a three-dimensional figure, is to really going to be building what's called a calculation triangle, which is a triangle inside of our three-dimensional figure. Now, what kind of triangle do you think we're going to be shooting to be able to make? Well, a right triangle, really. Why would we want a right triangle? Yeah, we have a lot of tools that we can use to find side lengths and angle measures inside of right triangles. Namely, we have the SOHCAHTOA and the Pythagorean theorem, right? Both of those things work inside of right triangles, and preferably, we'd like to come up with right triangles. Now, we do have some tools that we can use on non-right triangles. What are those? Law of sines and cosines. Very good. So on occasion, that might be more effective, but even often in those situations, you'd be able to do the problems using right triangles, even still. So really what becomes the trickiest part of this chapter is going to be these finding the right calculation triangle to use inside of these figures. And that's it. Really, all the calculation is quite easy, especially in comparison, and quite clear in comparison of like how you would do the solving or whatnot. So really the first part of this lesson today, I want to just talk about like what these calculation triangles are and how we know they're right triangles, just try to build a little intuition about if I'm looking at one of these three-dimensional figures, what am I really looking for? Okay? So let's say we have a right square pyramid like we have drawn here. An example of a calculation triangle could be this triangle CAB. Stop talking, please. How do I know that this angle A is a right angle other than the fact that I've written the right angle symbol there? So the height of a pyramid is going to be perpendicular to its base, or really any segment inside of the base, right? In the same plane as that base. Everybody's okay with that? So this might be one of a calculation triangle we might be interested in. Now, some of these calculation triangles are very obvious, and some of them are a little less obvious. When I say less obvious, it's mostly because when you draw the three-dimensional figure with perspective, so it looks three-dimensional, some of these angles don't look like 90-degree angles. So let's take this box here that I've drawn. Another name for a rectangular box here is a cuboid. So the pink triangle looks like a right triangle, right? That's very obvious that that would be a right triangle. The blue one is also a right triangle. What is the right angle in the blue triangle? It's G, right? How do I know that FGD is a right angle? So I know that the edges of my box meet at right angles, right? So this segment FG is going to meet the plane GHDC at a 90-degree angle. So it's also going to meet the segment inside of that plane GD at a right angle. Is everybody okay with that idea? So again, this is a situation where having a little bit of imagination, like closing your eyes and picturing it in 3 dimensions, really kind of helps, right? The two-dimensional, looking at it as a two-dimensional figure can be kind of misleading. If you kind of imagine in your mind's eye a box and these segments where they are, you'd be like, oh yeah, Yep, that's 90 degrees if you think about it. But this is typically the hardest part, is just being able to picture these things in 3 dimensions. Another example, let's say we have this triangular prism. So the pink triangle, easy to see that that's 90 degrees, right? The blue one is also 90 degrees. It also is a right triangle. Which is the right angle? B is correct. Again, we know that the edges of these prisms intersect the opposite face at a right angle. So this BG is in the plane of ABC. So this has to be at a right angle to BE. Does everybody see that? Okay. So again, 2 calculation triangles. Here, the blue triangle pretty clearly is a right angle, right? Looks like a right angle. The pink triangle is also a right triangle. What's the right angle on the pink triangle? F. Now, F does not look like a right angle in the drawing, but you have to picture what's going on here. AF is in the plane of the base, right? And we know that the height intersects the base at a right angle, so it has to be intersecting AF at a right angle also. Can we all see that? So let's look at a couple of numeric examples now. This first example says a shoebox is 32 centimeters long, 18 centimeters wide, and 11 centimeters high. We want to calculate the longest rod that'll fit inside that box. So imagine for a moment a shoebox, and what's the greatest distance or longest, how would you fit the longest thing possible inside of that shoebox? When you say diagonal, what do you mean by diagonal? A bottom corner to top corner, front, yeah, and on opposite side. So like the front corner to the opposite back corner, right? So the first thing I'm going to do is sketch a picture, and then I'll identify some calculation triangles and try to solve what I'm looking for. So here's my box. The rod that I'd be trying, or the longest thing I could put in here would be from like A to G, right? Everybody agree with that? So I'm going to build a calculation triangle that includes that segment AG. Does everybody see why that's a right triangle? Is there any other right triangle I could build that includes AG? There's not one. This is the only one you could do is like the top half of the same triangle, right? You could do like EAG, which is the same thing, really, right?
Yeah, that's fine.
All right, so let's look at what we know. So we know the segment GC. We're looking for AG. Do we know AC?
No.
Okay, so we can find AC, but we don't know it yet. Agree with that? It's not part of our given information. But Mark, you're correct. This is something we can calculate, right? So I can find a second calculation triangle to find the length for AC. What would that second calculation triangle be? ACD. Everybody cool with that? How would I find the length of AC? Pythagorean theorem. And once I have the length for AC, now I have enough information to solve for AG. Everybody cool with that idea? Okay. So this 36.7 is just the decimal approximation for this. It was much easier to get that. I couldn't get the square root symbol into my drawing. So I did that. And then we can just do the Pythagorean theorem again. Is everybody okay with that idea? How is that calculation? Pretty easy, right? Especially in comparison to what we've been working with. Massively easier. This is like as hard as it gets. The hardest part is really identifying the calculation triangle that you need to be using. That's really the hardest part. Okay with that idea? Let's do another one. So EABCD is a square-based right pyramid with side lengths of, where the square has side lengths of 12 and the height of the pyramid is 9.5, and we want to calculate EC. So I'm going to start by drawing my picture and finding a calculation triangle that includes the segment EC. So there's one. Is everybody good with that? Okay. We're convinced that that's a right triangle? Yeah. Should be easy to see that, right? We've used that one before in the examples, I think. Okay. Do I have everything I need to be able to solve for EC right now? We're missing something, right? What are we still missing? FC. So we're going to need to make a second calculation triangle to find FC. What calculation triangle can I use to find FC? I would use ADC and split AC in half. Why is it okay to split AC in half? So since the base is a square and a square is a parallelogram, I know the diagonals bisect each other. So the center of that square is going to be the same place as where the diagonals are bisecting. So that's a little bit of extra geometry. I don't expect you to be able to justify these things. More often not, in this kind of a situation, if it looks like it, it's probably that. If it looks like it's half of AC, it probably is. But that's the justification there. So you're correct. So we did that. So here's my triangle ADC. So I can use the Pythagorean theorem to find AC. And then we can just take AC and divide that in 2 to get FC. Everybody happy with that? Now that we have FC, we can find EC just by using the Pythagorean theorem again. Do we feel okay there? Again, not too bad, right? Once you get a little bit comfortable with looking at these things three-dimensionally and seeing those calculation triangles, they're not bad. They're not bad. Part B says to find the length of EM, where M is the midpoint of one of the sides. So I've gone ahead and drawn that and drawn in my calculation triangle. So we have EF that was given to us, that's the height. And we're looking for EM, so what's FM? Six. Great. Why is it 6? So the side lengths are 12. If F is the center of the square, then FM has got to be half of like 80. Everybody agree with that? Okay. So we have this, and I can just do the Pythagorean theorem. Is everybody okay there? Yes? Yeah, pretty easy still, right? Not bad, just lots of Pythagorean theorems. The hardest part is identifying the triangles that you need to use, but there's only so many in there to have to look at. Part C says, why are those two lengths different? Why is EM not equal to EC?
Because
okay, that's a reasonable explanation. I like the idea, if you take a look at the triangle EMC, that contains both those segments, right? That's another right triangle, isn't it? In that right triangle, EC is the hypotenuse, right? So it definitely can't be the same length as one of its legs. I think that's a nice explanation on that. But what Mark said here also, I think, is a good explanation as well. EF is the same in each of these two triangles, the pink one and the blue one, but FC and FM are different lengths, so the hypotenuse of each of those triangles definitely have to be different lengths. Everybody agree with that? You know, that's fairly commonsensical, right? So worth noting that this guy is a slant edge. That's one of the actual edges of our pyramid as opposed to EM, which is like the height of the triangular face, ECD. Can everybody see that? And that's something that, again, students commonly goof those things up, that they're the same length. They're definitely not. Next example. So we have this cone here. And we want to find the radius of the cone. So I've drawn in a calculation triangle here that includes the radius of the cone. What information do we know about this calculation triangle, BDC? So BC is how much? 11.3. Very good. And what else do I know?
That's nowhere near. Hold on, give me like.
Let me give you a hint.
37. What? Isn't angle C 37?
It is not 37.
Why not?
Well, because the angle ABC
Oh, I thought that was...
is that angle there. So you'd be correct if this was angle DBC, right? But you are correct that we are going to need to get an angle measure out of this. What angle can we get inside of that calculation triangle?
Wait, isn't it? You could get
So DBC is half of 53. That's correct. Why?
Because it's bisected.
How do you know that that's an angle bisector, that segment BD?
Because BD is the height. It goes, so it's right in the middle. I don't know.
So this segment can be perpendicular without it being an angle bisector.
Oh, because the height's always perpendicular to the... I don't know.
Okay. If I look at the triangle ABC, if I look at this triangle ABC, what kind of triangle is this? It's isosceles. That's the key. In an isosceles triangle, the altitude or the height is going to be this, also an angle bisector and a perpendicular bisector. It's everything. Only in an isosceles triangle does this work. If this triangle ABC was not isosceles, that would no longer be an angle bisector. Okay? So we need to have an isosceles triangle. If we're working with a cone, are we ever going to have a not an isosceles triangle? No. So, but you do need to be careful, because that's a common misconception students make, is you got to make sure you have an isosceles triangle if you're using that kind of thing. Okay? Everybody's happy there? So we have this situation. How are we going to solve for R? We're going to find DC by using sine, right? They're just a right triangle, so we can use SOHCAHTOA. So I can say sine 26.5 is equal to opposite over hypotenuse, which gives me 5.4. Everybody happy there? For that section, just 2. Let's now look at angles inside of these three-dimensional figures. This is going to be very similar approach to what we just dealt with. Okay, we're still going to be making calculation triangles and all that. Just this time we're going to be solving for angles instead of side lengths. So oftentimes when we're talking about the angle, we're going to want to talk about the angle between a segment and a plane or a face of our three-dimensional figure. So any segment inside of that plane is going to have an angle between that segment and the plane, right? So it's just wanted to point that out. You guys get what I mean? So some examples here of angles. We might be interested in finding the angle between the slant edge of our cone and the base of the cone. That would be the angle ABC. We might be interested in finding the angle between the height of our pyramid and the slant edge of the pyramid. That would be the angle ACB. Or we might want to be finding the angle between the internal segment, the internal segment AF and the face ABCD. This is base here. That ABCD is not a base for that prism. I don't know why it says that. Just a face. Yeah. Sure. Let's do some examples then with numeric examples. So, stop talking, please. Thank you, girls. Here we have a triangular prism. We want to find a couple of side lengths and then the angle that this line DE makes with the base of that prism. So I've gone ahead and drawn in a calculation triangle here. Everybody see the calculation triangle? Okay. But before we can use that, we don't know any of the side lengths on this calculation triangle. So let's start with maybe part A, EB. We want to find the height for EB. What calculation triangle can I use for EB? ABE is correct. So we know angle A is 21 degrees. What other piece of information do I know? AB is also 15. Good. So how can I find EB? Nope. Tangent. Because we have the adjacent side and we're looking for the opposite. So I can find that's 5.76. Sound good? How can I find BD? What triangle can I use for that? DBC, good. So I know DC is 15. What else do I know? BC is 23. So again, notice I drew that face in 2 dimensions where everything is squared off. It's a little easier to see the right angles then. So I can find BD just by doing the Pythagorean theorem, right? We happy there? Okay. Next up, we want to find ED. Well, this is very easy now. We know EB And we know dB, so just use the Pythagorean theorem. Right? No biggie. The last thing we're asking for now is this angle EDB. How can I find that? Well, I can use any of sine, cosine, and tangent because I know all three sides in this calculation triangle, right? I didn't write in the third one because, well, I decided to use tangent, so I just wrote in the opposite and adjacent. But really, you could use any of them. So I know that tangent of angle EDB is opposite over adjacent. And to find that angle, then I take the tan inverse of both sides. It gives me 11.8-ish. Remember that to find an angle measure, we're going to have to use an inverse trig function, right? If we're looking for the side lengths, we use the regulars. If we're looking for the inverse, or an angle measure, we're using the inverse. Okay. Let's do another example then. A cylindrical drum contains a stick that fits the diagonal exactly. The radius of the drum is 5.8, and the height is 15.8. Calculate the length of the stick. What calculation triangle would I use to do that? ABC. Very good. So BC is clearly 15.8. What's AC then? Yeah, 5.8 times 2, right? Or 11.6. So, Pythagorean theorem, and there's our diagonal. Everybody happy there? Okay. Part B says, what is the angle that the stick makes with the side of the drum? Which angle are we talking about there? It is ABC. Right? It's got to be with the side of the drum, not with the bottom of the drum. Everybody see that? Since we know the opposite and adjacent sides, we can do tangent. And we get 36.2. What do you guys think so far? We're pretty happy. This is massively easier than what we just finished with. Yeah, massively easier. Last example for today. And this is my favorite one because look at the great clip art here with that helicopter. A rescue helicopter is hovering 156 meters above the sea. It is dark and the helicopter is shining a light down onto the surface of the sea. If the diameter of the cone formed by the beam of light is 140 meters, what is the angle at the apex of the cone? So the calculation triangle I used here is LMN. And I'm going to solve for this angle LMN. And then how am I going to find then the angle at the apex, which is LMO? I'm going to multiply it by 2. How did I know that MN is an angle bisector? It's an isosceles triangle, right? It's a cone, so that the triangle there that we have is an isosceles triangle. Everybody cool with that? So I know the height is 156. We knew the diameter was 140, so that's how I got 70 for the radius. And we can just use tangent inverse to get 24 and change, and then we multiply by 2 to get our answer. Is everybody okay there? Oh, good. We're done.